and we have a router at the middle. So the link between the source and destination has a R bit per second data rate. So the source is going to push this L over R L bits packed into the R link. So each packet is going to transmit from the source to the router, and we need to wait the entire packet to arrive at the router so that we can forward to the next link. So in this case, the end-to-end link is going to be what is L over R is from this link, and the second L over R is from the second link, and total end-to-end delay is going to be 2 times L over R. Of course, assuming that there's zero propagation delay. So let's give an example, like just one hop delay. We have L, which is the length of the packet. Let's say is 7.5 megabits. And R, which is our link capacity, let's say is 1.5 megabit per second. So the delay is L over R. You divide the 7.5 over 1.5, and you end up with the 5 seconds. So that means in order to transmit this packet, which is 7.5 megabits, through this link, which has a capacity of 1.5 megabit per second, it will take to 5 seconds to transmit all these packets over this link. So that's why the delay is an important performance metric in the network. Of course, we have some problems when we, transmit these packets. One of them is the queuing delay or packet loss. So what is the condition for the queuing is if your arrival rate is much more than, is more than link capacity, then you experience the queuing. So what's the queue is basically because your rate is much more than the transmission rate. So you need to put some of the packets in the buffer in order to wait for their order. So in this case, the packets will queue and wait to be transmitted once their turn comes. So if there are a lot of kind of packets that are waited in the queue, sometimes these packets can be dropped. In other words, will be lost if your memory or buffer is full. Okay, so if your memory or your buffer is fills up, then the packets can be dropped in this case, or it can be lost. So that's what we call packet loss. And there are two key network core functions at the network layer. The first one is called routing. The second one is called forwarding. So what's the difference between routing and forwarding? So the routing is governed by the routing algorithms, and the forwarding is governed by the forwarding table, as you see from here. So what's the routing? It determines the source destination route that is going to be taken by the packets. But forwarding is kind of an internal process. It moves the packets from router's input to the appropriate router output. Okay, that was about packet switching mechanism. Let's talk about the alternative core structure, which is called circuit switching. This is one of the old-fashioned switching that we use in the telephone line in the past. And currently still some people are using this switching technique. So in this case, end-to-end resources allocated to or reserved for a specific call between source and destination. So as you see from here, let's say this device is going to talk to this device, and we first of all we're going to set up a specific route. So this is a specific route, in this case the second one, and it goes to the first one and then reach to the destination. So we set up a physical link. This is a physical link. In the packet switching is totally virtual, so the paths are virtual. But in this case, first of all we set up a specific link between two devices. So that means this channel, this link is gonna be allocated, reserved for this specific communication. Nobody else can use. That's why it's guaranteed performance. There's no shading. And that's why the performance is better than packet switching. But in terms of capacity, because only these two devices gonna use this link, then in terms of efficiency is not an efficient mechanism. So in other words, this circuit segment is idle if not used by call. And this is being used by the traditional telephone networks that we have at our home or offices. In circuit switching, we have two different types of multiplexers. The first one is called frequency division multiplexers. The second one is called time division multiplexers. As you see, let's first explain the FDM. We have a channel, a link. So we divide this channel into the sub-channel. Let's say, assume that we have 4 users. Let's say we have 4 megahertz channel. So we divide equally among these users. So that's why we allocate 1 megahertz to each user. So this channel is gonna be for blue user. This is gonna be for green, and this is gonna be for yellow, and so on. So each user is gonna have their own sub-channel, and they can utilize anytime without waiting other users. But they're gonna use only 1 megahertz. In case of TDM, let's use the same example. We have 4 megahertz channel, and we are gonna use this 4 megahertz channel one by one. So time division multiplexers. Let's say we have 4 users. We are gonna split the time into 4 time slot. The first time slot is gonna allocated to the blue user. Once he completed to utilize this full channel, which is 4 megahertz, and then the second user, green user, is gonna use the full channel, which is 4 megahertz, and then the others and the others. So the main advantage of this TDMA is when a user turns calm, it can utilize the whole channel, which is 4 megahertz in our example. But the main disadvantage is that they have to wait other users to complete their transmission. I guess it's clear, right? Okay, let's summarize by comparing the packet switching versus circuit switching. So first of all, we can clearly say that packet switching allows more users to use network. Let's give an example to support this claim. So first of all, let's say we have 1 megabit per second link, and we have 10 users. So in case of circuit switching, we just equally, allocate. Let's say each user is gonna have 100 kilobit per second when they are active 10% of time, assuming that. So in this case, we support this. We support 10 user maximum when we have 1 megabit per second link. But let's calculate this for the packet switching. So we can support up to 35 users with the probability of 10 active at the same time is less than this probability. So in summary, so we can support up to 35 users compared to the 10 users in the switching, circuit switching, under, of course, certain conditions. So in circuit switching, we can support 10 users. In packet switching, we can support up to 35. Because in circuit switching is a dedicated, it's just reserved for a specific users. But in case of packet switching is a virtual, it can be utilized based on the best effort strategy. Packet switching is great for the bursty data because we share the resources. It's simpler compared to circuit switching. No call setup like in circuit switching case. Excessive congestion possible in case of packet delay and loss. And therefore we need protocols for supporting the reliable data transfer as well as congestion control. And so the question can come to your mind, how can we provide a circuit-like behavior in packet switching? First of all, bandwidth guarantees needed for the audio-video multimedia applications. It still is in an ongoing problem. People are still doing research to answer this question. So we are going to cover this question in details in chapter 7. So you can imagine or think like circuit switching is a reserved resources compared to the on-demand allocation in the packet switching. Okay, so let's talk more about the internet structure in global level. As we mentioned, is a network of networks. So and system connect to internet via access ISPs. This can be a residential company and university ISPs. And at the end of the day, access ISPs must be internet connected so that you can reach to the other part of the network. And the resulting network is very complex. So we are talking about the millions, now billions of the devices that are connected. So it's a complex structure. And the evolution of the internet is driven by the economics as well, the national policies. So let's look at the current structure of the global internet structure. As you see, as I mentioned, we have millions of devices, even the access ISPs. So how shall we connect these ISPs so that we can talk to each other at the global side? So one of the first straightforward solution is to connect each ISPs to each other, right? Which is like this. But what's the problem? Connecting each access ISPs to each other directly doesn't scale. So it's gonna have O and square connections. So this is really complex to manage. So that's not a practical solution. Okay, another solution is, which is kind of more like a layering, to connect each access ISPs to a global transit ISPs. So instead of this is the second solution, which is more practical. So access networks are connected to the global ISPs. And as you see, we have a global ISP, and each access network they're gonna connect it to each other. And even we can split this ISP into multiple ISPs, ISP A, ISP B, ISP C, so that we can, form a competition. And they must be connected, these ISP A, B, C, the global ISPs. Of course, they must connect to each other, which through the peering link or IXP link. So that's why we come up with a structure to manage this very complex internet structure around the world. So one of them is to utilize the regional networks. So as you see, the regional networks may arise to connect access networks to the ISPs. And on top of that, we have some content provider networks, such as Google, like YouTube, Microsoft, Akamai, and this kind of content provider networks, Skype, they may run their own network to bring services to their end users. So to summarize, we divide and we come up with a structure that we have tier 1 ISPs at the top, and then we have the regional ISP that are connected through the IXP link. And on top of that, we have content provider network such as Google, YouTube, or Microsoft Skype. They provide their own network. And then these regional ISPs, they are connected to the access ISPs. So basically, we come up with a structure so that we can manage this very, very complex network around the world. These are some, tier 1 ISP from United States, from Sprint. It's an operator at the US. Okay, that was about the network core. So the next topic is how to measure the performance of a network. As I mentioned, there are 3 performance metrics that we use commonly. The first one is the delay, the second one is packet loss, the third one is the throughput. Let's look at those parameters quickly. Then we will cover later on throughout the semester in another chapters. So how do loss and delay occur? I just mentioned briefly. If your packet arrival rate to the router is greater than the link rate, then we will experience the queue. So the packets are going to wait in this queue in order to be transmitted. But if the buffer fills up, then these packets may be dropped, and then you lost these packets. That's how the packet loss and delay occur at the router. 4 sources of the packet delay. When you talk about the delay, we have 4 parts. The total delay is called D nodal, which is equal to D processing plus DQ. When I say D delay, transmission delay plus propagation delay. So this D processing, as the name implies, is the processing, the delay that takes during the processing. And then we have the Q delay, as I mentioned. So when the queue happens, the packets wait. This is the time that elapsed during this wait. And then we have the transmission delay when the router start to transmit the packet by feeding to the link. This is called transmission rate delay. And then we have the propagation delay. After you feed into the link, and this is the times that takes from the router to the destination. So, and this the physical, it depends on the media. If it's a cable, is different. If it's an air, is different. So, which we call propagation delay. Okay, so processing delay, we talk about that. It checks the bit errors because it applies some algorithms. So when you apply these algorithms, it takes sometimes which introduce some delay. We call it processing or nodal processing delay. It determines the output link, which output link is gonna send. And this delay, processing delay, is typically less than millisecond. The queue delay we talk about already, it depends on the congestion level of the router. So when we ask a total delay, you need to calculate all these processing delay, queuing delay, transmission delay, and propagation delay, and then add them up. Transmission delay, as I mentioned, how to calculate is the L over R. L was the packet length and the R was the link bandwidth. And propagation delay, you know, is equal to D over S. What's the D is the length of the physical link in terms of meter or kilometer. So actual, you know, distance between this transmitter and receiver. So which we call D over S. S is the propagation speed. If this electromagnetic wave is equal to 3 times 10 to the power of 8 millis per second. So as you see, the transmission delay is different than propagation delay. Some example to how to calculate this. Just going over. Okay, queuing delay, let's look at here. R was our link bandwidth, L was packet length, A was average packet arrival rate. Average queuing delay, as you see, traffic intensity. If the traffic intensity increases, of course, the average delay, queuing delays increases exponentially. So let's look at this. If this traffic intensity close to 0, as you see, the averaging queuing delay is small. But when this traffic intensity close to 1, average delay is going to be large. If this traffic intensity is greater than 1, that means the more work is arriving than can be served. So average delay is going to be infinite, very high. How do we measure the real internet delays and routes? We use different kind of protocols or program. One of them is traceroute. So through the traceroute, you can calculate this delays in the internet. And this is one of the snapshot of this traceroute. So you can check by yourself this kind of delays in the internet. Packet loss. So how this, under what condition the packet loss happen? When the queue in buffer has an infinite capacity, finite capacity, sorry. So assuming that buffer has a finite capacity and packet arriving to full queue is dropped. Because there are many, the arrival rate is much greater than the link transmission rate. So the queue is gonna start to swallow, and then after some point, so we start to drop the packet, which is gonna lead to the packet loss. But we have a different solution for this problem. So one of the most common solution is to initiate the retransmission mechanism. So if you experience a packet loss, then we ask this packet to be retransmitted. And so we will talk about all this problem and solution in the future throughout the semester. I'm just giving an example. We have the throughput. What's the throughput? It's the rate, data rate at which bits transferred between the source and destination, sender or the receiver. So this throughput can be instantaneous or it can be average over a long period of time. Okay, throughput, there are some problems, per connection, end-to-end throughput. So if there are some bottlenecks, so some important intersection, the intersection of this, the capacity of these intersection devices must be designed very well. Otherwise, you experience some bottlenecks, some congestion. Sorry. Okay. Another topics that we are gonna cover in this course is called protocol layers and servers models. As you see, the internet is very complex and it connects millions of billions of devices. So, and it has many components. It has host, it has routers, different types of cables, medias, applications, protocols, hardware, softwares. It's very complex structure that we are talking about. So the question is how to manage efficiently or organizing this kind of structure. One of them is, before I answer the question, let me give you an example. How, in the net, that was a question about the network. And we have similar kind of large organization in different areas, such as in the air travel. Air travel is also a complex organization to manage, right? So when you start to travel, let's say from Istanbul to Ankara, so what do? Let's follow up the steps together. First of all, you purchase a ticket, right? Either you call the customer service at airlines, right? Or over the mobile internet, right? To purchase a ticket, air ticket. And then, so once you purchase the tickets, when your flight date comes, you go to the airport and you check in your baggage, right? You deliver your baggage to the air travel company. And then after you run and walk to the gates so that you can walk into get on the airplane, and then the pilot is gonna runway and take off and fly from Istanbul to Ankara through a specific airplane routing, right? And then it land to the Ankara airplane through this route, and then it goes taxi and runway, land and to the specific gates, and you get off from the airplanes, from a specific gates, and then you go and claim your baggage, collect your baggage. And if you have any question about ticket, you complain ticket through the phone or internet to the airplane company, right? As you see, even a travel from one point to another point through the airplanes, it consists of many steps, a series of steps. So the question, can we do all these tasks within a single point? When I say single point, let's say it's gonna be pilot. Pilot is gonna, sell the tickets. It's gonna receive the calls and listen to the complaints. It's gonna collect the baggage. It's gonna, guide the, the passenger to the gates. And on top of that, it's gonna, use, airplane, right? It's gonna ride the airplane. So can a single person do all these complex tasks? So the pilot will not accept, and pilot cannot take all these tasks basically, right? So that's why we split this task into different departments, different layers. So that's what we call layering. In order to manage such complex organization, so we need to split the structure into the layers. So that's why layering is one of the solution, right? And each layer implements a service. So only there's a ticket department, there's a baggage department, there's a gates department, there's a pilots, and so on, right? So that's why we handle these such complex organization efficiently. So each layer is gonna rely on the other services, right? So first of all, the ticket office is gonna rely onto the baggage office is gonna rely onto the pilot, and so on. So why we need a layering is one of the efficient solution to deal with the complex systems. So explicit structure allows identification relationship of complex system pieces, right? So that's why we apply this layering solution to the network as well to manage such huge and complex internet structure around the world. And it also helps to easily maintain and update the system, right? If you say, okay, I'm gonna upgrade the whole internet tonight, that's gonna affect the whole world, right? But if you have a layering, you just say, I'm gonna upgrade just that specific layer, then, majority of the people will not be affected from this maintenance or upgrading. So layering is also good when it comes to the maintenance or upgrading the system, or any kind of change in the procedure is not gonna affect the rest of the system. So similar things is applied to the internet. So that's why we split the internet protocol stack into the layers. The first one is the application layer, which support the network applications such as FTP, SMTP, HTTP, email, social networks, and so on. All the applications are run at this level. Then we have the transport layer. It's responsible for the process-to-process data transfer using a specific protocol such as TCP/UDP. Then we have another network layer, which is the network layer, is just responsible for routing the datagrams from source to destination using the IP or routing protocols. And then we have a data link layer, which is just responsible for data transfer between the neighboring network elements using the Ethernet or the 802.11 Wi-Fi. And then we have the physical layer. It just deal with the bits and transmit the you convert your bits into the signal and signal through the cable or the over the air. So as you see, each layer has a different functionalities that complement each other. That's what we call OSI reference model. So it consists of application, presentation, session, transport, network, link, and physical layer, 7 layer. So presentation, it allows application to interpret meaning of data, kind of encryption, compression, machine-specific conventions. And we have the session layer, which is responsible for the synchronization, checkpoint, recovery of data exchange. So this is the popular OSI reference model that we use. There's another concept which we call encapsulation. So when we start to take the messages at the application layer, then we encapsulate at each layer to pass through the physical layer. So let's give an example. Let's assume that you have an application such as WhatsApp. So you're sending a message. This message is gonna be hand over to the transport layer. Transport layer is gonna split into the segment. So it was a message. Now it becomes segment at the transport layer. And we put a header at the preamble. And then we pass to the network layer. Network layer also is gonna form a datagram. So the segments become datagram. And we add a header, network layer header at the preamble. We encapsulate and we pass to the data link layer. Data link layer, it's gonna convert into the frame. And we add the new header for the link layer. And then we pass over switches at link and physical layer. And then to a router. So the router consists of 3 layers, including the network. So it's gonna remove this header one by one to the network layer and then pass to the destination. And in the destination, we apply the reverse operation. Starting from the physical layer, we remove the physical layer header and pass this to the upper layer, which is the link layer. And then link layer is gonna remove the header and then pass to the network and then so on up to the application layer. So when it's reached to the application layer, we see the original message that we sent. Any question, guys, so far? Is it clear? Actually, these are the summary of the things that we are gonna teach in this course throughout the semester. So we will go to the details later on. Okay, another important topics that we're gonna learn in this course is gonna be security of these networks, right? When you say security, we have different types of security. We are talking about the network security, field of the network security, how the bad guys can attack your computer networks. And then if they attack, how we can defend the networks against such threats. And then how to design architectures that are, kind of immune or robust to such attacks and threats. So originally, the internet is not designed for, security in mind. So they at that time they didn't expect that such attacks are gonna happen. But as the internet grows up, we see such threats in terms of security. But as the internet grows up, so the internet organization is considering security at all layers. So there are different kind of bad guys in the networks. Malware, for instance, is one of them. The malware can get in host from virus or the worm. What's the virus? Is a self-replicating infection by receiving and executing object, mostly by the email attachment you are infected. The worm is also another self-replicating infection by passively receiving object. And then we have spyware, we have the malware, can record keystrokes, the websites that you visited, and upload information to collection site. So, and the infected host can be enrolled in botnet used for spam. And then you can experience some DDoS attacks. What's the DDoS attacks? So the bad guys in this case can attack server, network infrastructure. One of the most common attacks is, in this case, is denial of service, DOS. How does it works? How these attacks happen? First of all, the bad guys select a target. Let's say this is our target that we're gonna attack. The bad guys, they're gonna attack to this server. So it's breaking to host around the network and send packets to the target from this compromised host. So this is how the denial of service happen, because attackers make resources unavailable to the traffic by overwhelming the resource with the bogus traffic. So it basically overload the target with a lot of traffic so that it cannot respond to this request. Another one is bad guys can sniff packets. What's the packet sniffing? It's like a smelling, right? They can, for instance, we have a computer server A, we have a client B. So there's a bad guy between A and B, which is the C. So it can sniff these packets between B and E. For instance, the Wireshark software is a free kind of packet sniffer that you can use. You can, intercept a packet between two computers and try to analyze it. So we use a Wireshark for that purpose. Another type is bad guys can use fake addresses through the IP spoofing. So it basically sends a packet with false source address. So it intercepts and it can change a source IP address. And then we can discuss this type of attacks later on in chapter 8. So the last topic for introduction for today is the history of the internet or network technology. Let's look at some milestones in this internet history. In 1961, the queuing theory shows the effectiveness of the packet switching. And we have one of the first military networks in military networks, they use the packet switching. In 1967, we have ARPANET that is conceived by the ARPA in US, which is called Advanced Research Projects Agency. And in 1969, we have the first ARPANET node that is operational. And then in 1972, first public demo for this ARPANET. And then we have a network control protocol for the first host-to-host protocol, first email program in 1972. And the first ARPANET was consisted of only 15 nodes. Now we have a billions of nodes. And let's look at between 72 80, Aloha Networks satellite network in Hawaii was developed. What else? In 1979, remember in 72, they have only 15 nodes. After 7 years, it becomes 200 nodes. Okay, in 1983, one of the important milestones, the deployment of TCP/IP protocol. In 82, SMT email protocol defined. 83, we have the DNS, domain name server. And then in 85, the FTP protocol defined. 88, we have the TCP congestion control feature. In early 90s, ARPANET is decommissioned. And then now we have NSF net. And then in early 90s, in parallel, the web, World Wide Web is start to develop. And the HTML, HTTP, you know, and the browser. In this time, we used Netscape. I don't know, you guys don't remember basically. And then in late 1990s, the web became commercialized. And then other development in 2000. And from 2005 to present, we have millions of host tablets, computers connected to the internet, the search engine, service providers, e-commerce, all these things, you know, developed. Okay, so that was the, you know, introduction about this course. So I try to summarize what we're gonna learn throughout this semester. Okay, guys, that's all for today. Any question?
Not for now, sir.
All right. Thank you, guys, and I'll see you next week. Take care.